Okay, thank you very much, everyone, for coming back for the afternoon session. So we begin the research talks. Jean-Christophe, Jacob, and we asked our speakers to have an emphasis on some open problems and new directions throughout these talks. And our very first speaker is our Eisenstadt chair for this program, Isabelle Gallagher. She will speak about mathematical analysis of dilute gases, derivation of the Boltzmann equation, fluctuations, and large deviations.
Thanks very, very much for the invitation. I'm really very happy to be here. Like a lot of you, I guess it's sort of my first outing out of home. So I'm really happy to spend some time here and to give a Blackboard talk. So I hope I still know how to do that. But okay, tell me if anything's wrong. So I do get, for some reason, 2 slots. So I'm very lucky. You're probably much less lucky, but that's life. So I'll be giving one talk today, one tomorrow, and even I think even one on Friday, but that's more like a general public. So you're more than welcome to go and visit Montreal if you like at that time. But anyway, so the 2 talks today and tomorrow will be on a research project I've been having for many years now with 3 collaborators who are Thierry Bodino. So I guess it's like a little bit like Jean-Christophe for Scotland. He's my probabilistic lawyer, but he's not here. So whatever I say is wrong, and it's not his fault, it's mine, obviously. So he's taught me the little I know on probability theory is due to Thierry, Laure Saint-Raymond, and Sergio Simonella. So what I'll try to do in these 2 talks is sort of present what we're trying to do, what works and what seems to be working and what's not, and try to give you some open problems as I go along, okay? More or less difficult, I'll tell you from my point of view, at least what I think about those problems. And so I'll try not to go too fast. I know one of my habits is to go too fast. And this domain is sometimes a little bit technical, so I'll try to take my time. I do have 2 slots, so I'll try to go slowly. Please tell me if you think it's going too slowly or if it's going not slow enough. Okay, please. So stop me whenever you like. So Jean-Christophe, you can do the same as what you did this morning. Was perfect. So I know you practiced a lot, probably your duet. But you can improvise with me, it'll be great. So please stop me whenever you like. Right, so let's start with the general context of our work is to try to study something which is related to Hilbert's 6th problem. Broadly speaking, the question is the following: you're looking at a gas, okay, dilute gas. We'll define that later on. And so, as you know, there's one way of describing how the gas is evolving in time and space is writing down fluid mechanics equations. Right, so I guess a lot of us know the Euler equations, maybe Stokes equations. That's equations that are used all the time to model fluids. And there's another way you could describe fluids would be by studying just the evolution of each particle of the fluid. Okay, and so you can assume that just to make things as simple as possible, which we'll be doing here, that all the particles are just atoms, and actually they're even spheres. Okay, and they just move in straight lines and they collide very often. And you can write down all those equations. Okay, so that's the atomistic point of view, write down the equations for the atoms. And then you have the fluid point of view, write down the Navier-Stokes equations. And both models are describing exactly the same thing, which is the gas in the stream. Okay, so the question Hilbert was asking was, is there a way of connecting both descriptions, the microscopic description and the macroscopic description, by some kind of a limiting procedure? Okay, and what he asked in, I think it was 1900, ICM, you probably don't remember, I don't either actually, but he did give those 23, neither is you, right? Okay. So if you weren't there, right, no one was. This is going to be horrible. I know. Okay, just go ahead. Okay, so he gave this list of 23 problems. And the 6th problem was that question I'm asking you. And actually, his problem, in the question he asked, he said you could use Boltzmann's equation in some sense to relate both microscopic and macroscopic equations. That's exactly what we'll be doing today. So, I mean, if you want one huge open problem, the open problem in this context is answer the question. Okay. Hilbert's question, go from atoms to fluid mechanics. But okay, that's very unreasonable, I guess. as a question. But so what we've been trying to do for many years now is, first of all, so you go from this microscopic description to the macroscopic. Okay, so that's the question. And in between somewhere, you have what we call the mesoscopic description, which is precisely the Boltzmann equation. So what I'll be doing in those in the two talks will be explaining especially this limit here. That's really what we've been trying to do. Tomorrow I'll talk a little bit probably about what can be done in this context, and some things can be done, not very much. That will be for tomorrow. But today I'd like to concentrate on this limit, and especially what we've been trying to do for a few years now is trying to understand what's around the Boltzmann equation. In some sense, as we'll see, it's known that the microscopic model converges to the Boltzmann equation in a very restricted framework, which is very bad, but I'll try to explain why later on. But that's sort of understood. And so to go beyond that understanding, to go to fluids in particular, what's interesting in some sense is to understand the errors around the Boltzmann equations, the fluctuations. Okay, so this is something we've been doing rather recently, is fluctuations and large deviations, and I'll try to talk about that today and tomorrow. Okay, right. So to start, fine. So let me show you the model, the microscopic model. So, so as I said, we're looking at hard spheres, and so there are a lot of atoms, of course, in this room. So the number of spheres is enormous, and to study it and to get to Boltzmann equation or the fluid mechanics equations, you have to do some kind of averaging. Okay, you're not going to follow each particle individually and find the fluid equations. You have to average in some way, and actually there are several levels of averaging. And the first one will be on the number of particles. Okay, so there's no reason why you should know exactly how many particles are in this room. Okay, so I don't think we do. We know how many particles, and we don't care actually. So I'll call n, calligraphic n will be the number of particles, which is a random variable in some sense, which will be satisfying a kind of Poisson process. Okay, and what will be interesting and important in our problem here is the average number of particles. Okay, so what should be the average number of particles in this context of dilute gases? So a dilute gas means essentially that if you take any particle in time one, it's going to cross another particle. Okay, 1 or 2 or 3, but not very much more. Okay, so the gas is not very dense. So if I assume that each particle is going to cross another one in time one, what does that mean on the number of particles? So let me call epsilon their diameter. And let me just look at one particle of diameter epsilon. This is a small particle. And assume it's moving in a straight line. Okay, so the volume it's going to occupy in time one, if its velocity is roughly 1, is going to be something like epsilon d minus 1 in dimension d. Okay, so I'm in d space dimensions, d is 2 or 3, for instance. So this is the volume of the cylinder my particle is going to cover in time 1 if it has velocity 1. And if I want to be sure this particle is going to hit another one, what I need is that the number of particles, the average number of particles, which I call mu, times epsilon d minus 1 should be roughly equal to 1. Okay, so mu epsilon will be the average number of particles. And this scaling here is known as the Boltzmann grad scaling, and that's just the assumption we're going to make for the whole talk. And in this whole theory is that the number of particles scales like epsilon to the 1 over to the minus d minus 1. Okay, so mu and epsilon will be going to 0 and mu epsilon to infinity. Yeah.
Probably just a dumb question, but yeah. Oh, I have a so when you say average number of particles, is it sort of like a box of total volume 1 or something?
Exactly.
So equivalent to density.
Exactly. That's absolutely correct. Thank you. Okay, so that's my first easy enough average. And the next thing I'm going to do is write down equations and then see what object I want to study to get to the mechanics equations. So my particles here have a center which I'll locate in some point xi. And for all this business, I'll assume my particles will be in a periodic box of size 1. Okay, so TD is a periodic box of size 1. Everything I'm going to say essentially is true in the whole space. And nothing I'm going to say is essentially true in any other situation, at least you don't know. So first open problem. Could you replace this by anything else? Which of course physically makes sense. So there are a few recent results. If, for instance, an exterior of a convex domain, Théophile Dolmer, who was a PhD student of mine, and Laurent Devilette managed to derive the Boltzmann equation in that case. And that's essentially the only case where things are known. Okay, for reasons we can discuss as we go along in the talk, but for everything I'm going to say, it's definitely periodic or the exterior of the convex domain. That's much more difficult in that case. So here are the positions of my particles, and I is going from 1 to n, number of particles, and their velocities will be called vi, and they're in the whole space, and they're related by Newton's laws. So Newton telling you that the time derivative of the position is the velocity, and the time derivative of the velocity is whatever you like, and for us today will be 0. Okay, so it's the simplest possible model. There's no force, right? So again, open problem. Can you put a force? So you could put a potential here, well, some force. If it's compactly supported, and what else? And decaying. And essentially, everything I'm going to say today is true. This has not been checked all the way. I know it's true to derive the Boltzmann equation. That's a fact. And I suppose everything else I'll say is also true, but no one has really done it. Okay, it's just terribly technical. Yeah.
Are n and u epsilon the same since they're the torus? Am I crazy or am I?
No, I have to average. N is a random variable. Okay. I'll give you in a few seconds the probability measure. So it's not exactly the same. Okay, so if you take any other kind of force, if it's not compactly supported, there's a student of Laure Saint-Raymond who proved that you can derive the Boltzmann equation if the decay is like a triple exponential at infinity. Okay, in space, 3 exponentials of minus x, then it works. I guess 3 exponentials will come at some point tomorrow. You'll understand why. So it's okay. It's the best you can do for the moment. So obviously, there's a lot of work to do in that case. You could also wonder, from physical reasons, it would be very interesting to have forces which are not decaying. Okay, in general, you can have forces that have some kind of a more complicated interactions, are a little bit more complicated than just repulsive interactions. And so definitely that would be very, very interesting. But for the moment, nothing, to my knowledge, nothing is known rigorously in this context. Okay, so this seems very nice. I mean, they're going in straight lines. But as I said, my particles are also colliding. Okay, so it's not exactly as simple as that. The equations have to be supplemented with the fact that if 2 particles collide, so let's say particle I is hitting particle J, okay, then I have relations between the outgoing velocities, which I call VI, Vj, and the incoming velocities, which traditionally we call V prime I, V prime J. And the collisions will be elastic. Again, open problem, can you do something else than elastic? And that's, I really don't know, it's really hard actually. I have been struggling for some time to try to derive the Boltzmann equation for non-elastic collisions, and it just doesn't work. But we can discuss that at some point if you like. But anyway, so the relations between those 2 velocities are that the incoming velocity is related to the outgoing one by simply the Descartes or Snell-Descartes laws. So if I call omega ij the unit vector relating the centers of both particles, then this is what you get, and V prime J is the same with a plus sign here. So as an exercise, you can check that this, yes?
When you say that, I mean, how do you think about it not being elastic?
I mean, you lose energy.
You lose energy,
Yeah.
not with the angles,
No.
not with the reflection.
No, I mean, you lose energy. Yeah.
The point is that I mean, there are equations that people have written down trusting those routines, but the
Definitely.
issue
The issue is just deriving those equations.
But you trust, like,
Of course.
you're trusting.
Yeah, the equations are fine.
The equations are right.
Yeah, the equations are right. I'm sure,
It's more math.
but just we don't know how to get from this to the, Boltzmann and elastic exists, and people have been working on it for a long time, and they get also the hydrodynamic limits from those equations. But deriving the equation is still open. So omega ij is just a vector relating the center of these hard spheres. So this is a purely deterministic system, and that's important in some sense. A lot is known, And I'm not an expert, so I won't tell you exactly what's known unless you force me, but and I'll probably say things that aren't totally correct, but a lot is known in some sense when, for instance, if the velocities after collision are taken in some random way with some law, then you can find in some, not an easy way, but it does work to get the Navier-Stokes equations, for instance. Yeah.
When you say deterministic, do you assume that Wij are none?
Yes. Oh yeah, this is just this guy is xi of t minus xj of t over epsilon.
Agree.
Exactly. So you could assume it's random, and then that would help in some sense. Exactly. So here everything is purely deterministic, and omega is exactly the distance between the sides. So what we'll be interested in today in this whole business, the empirical distribution, I call pi epsilon t, which is simply 1 over mu, the sum. So I haven't exactly defined why mu is the average of n, but that will happen in a second, of direct mass at the positions and velocities z. So I'll call z epsilon. I didn't put any epsilons. Okay, so I should put epsilons. Just to remember, all these guys depend on epsilon. So zi will be just the position and the velocity. I call z the couple position velocity. So we'd like to know how this thing behaves in time as epsilon goes to 0, whereas mu epsilon goes to infinity. And now let me describe the next level of averaging, which is the fact that we don't know exactly where each particle is at time 0, whatever time 0 means. Okay, so I just decide to look at my gas now. I don't know how each particle is distributed. What I'm going to assume is that they're all identically distributed. And my initial, so the only random feature in my problem in some sense is that the initial distribution of my particles, which I call W, is given by this formula here. So let me just explain it slowly. So capital Z means a collection of all small z's. Okay, so this will be a collection of Z1 up to Zn for any n, and Zi will be positions and velocities. So let me just write down what this is and then describe it. So by definition, I'm going to assume that the number of particles has average mu epsilon. So this looks like a Poisson process. Okay. And then I'm going to assume that each particle is identically distributed at time 0, which means I have the product I going from 1 to n of f0 of zi. Okay, so each particle is distributed according to this f0, which is a probability distribution, so non-negative and the integral 1 function. And now I'm almost done, except that I have to remember that this distribution function here is concerns these particles here, and particles aren't allowed to overlap. Okay, whenever they touch, they collide. So Zn here is living in a world where particles don't overlap, which I call d epsilon n. By definition, is a set of all Zn such that if I is different from j, then xi minus xj is larger than epsilon. So I have to remember here that I have this assumption. Okay. And now I just have to renormalize everything. Okay, so this guy is guaranteeing that this guy here is of average 1. This is the only, in some sense, averaging in this whole business is that whenever I'm going to compute something, it's going to be with respect to this measure here. So if I compute expectations, what I mean is that I'm going to sum over n, integrate all this. Is that okay? Probability, p epsilon, will be with respect to this measure. Okay, so I assume here that f0 is of average 1 and is non-negative. So my system is deterministic, but what I don't know is the number of particles. I only know their average. And what I don't know is their distribution. I just know initially they're distributed according to some f0, which I know, but I don't know anything more. And so I'm going to evaluate everything with respect to this measure. What questions could I ask? So I guess question 1 will relate to the Boltzmann equation. In some sense, a law of large numbers. If, let's see, how can I describe this? If I want to understand, given some test function h, okay, the empirical distribution, yeah.
The second line, the thing that's being inverted, what is it?
Okay, so it's just a thing that's guaranteeing that the average, that the integral of this guy is 1. So it's just a sum over n. of all that. Integral of f0 n times. If you didn't have this exclusion, this thing is sort of a pain, right? If you didn't have that, then z epsilon would just be the exponential of mu epsilon as usual. Okay, but because of the exclusion, it's a little bit more complicated. So where is the Boltzmann equation hiding?
Sorry, what does Wn represent?
That's the definition of my initial distribution. Okay, that's whenever I average, it's with respect to this distribution.
Okay.
Okay, it's my measure, my initial measure. Okay, and so you could wonder what happens as time goes on to this guy, for instance, which we'll be talking about later on. But everything I'm going to, the averaging procedure is with respect to this measure. So for instance, okay, so question 1, which will be a theorem in some time, will be what's the probability? So there is essentially 2 questions here. That if I take any test function h, I look at this empirical distribution computed at h, and so what Boltzmann in some sense claims, and we have to prove. So everything depends on z here. If I take h a function of one variable, I don't know who f is. Well, I do know who f is. F is the solution of the Boltzmann equation, right? But we have to prove that. So the first question you could ask is there a function f such that the probability that the empirical distribution at time t computed at h, that this guy is larger than delta, would go to 0 as mu epsilon goes to infinity for any delta. That's a law of large. First thing we want to address, and that's exactly actually the derivation of the Boltzmann equation will be that. What we'll check is that this f satisfies the Boltzmann equation, and this theorem, well, there is a theorem saying essentially that. Well, we'll state the theorem a little bit later. In some sense, well known, although there are a lot of drawbacks to what's known. Then if you believe that this is true, then you can just use the usual questions people ask in probability theory. Once you know you have a law of large numbers, you have a central limit theorem. And plus the central limit theorem here, we'll just multiply everything by essentially the square root of mu, which is the number of particles. And so you could look at what's the evolution in time of this object here. You take the empirical distribution, remove its average. That's a fluctuation field. And you want to know how this involves in time. That's a central limit theorem. That would be more like the law of large numbers. Okay, so the first question is, what's the average behavior of a typical particle? Is it the Boltzmann equation? Second question, how are fluctuations around this average behavior? Describe that. So that's a little bit more recent. And then question 3, which we'll see if we can address it or not, would be a large deviations, which roughly would mean what's the probability that actually you're totally wrong, that your empirical distribution looks like something else. So I won't be too precise here. Okay, so as a distribution. Okay, do you have a large deviation functional saying that this thing would look like? So that's a question we'll try to answer maybe. So if you have a large deviation principle, then the probability that this empirical distribution looks like something else and not a solution to the Boltzmann equation should look like something exponentially small with some functional here to be computed. Yeah.
In question 2, you chose to compensate by the expectation, but you could have compensated by the F.
You could, but okay, let me think. It gets more tricky, I think. I mean, yes.
But we know like
we oscillated a lot between both formulations. In the end, this one works much better. So maybe it works with the F, but I have to think much more. Okay, I'm not so sure. Because you don't, I mean, the rate of convergence here is not so good. So I'm not sure it works. Yeah.
Should the large deviation, is it implicit that it depends on F2 or it's Q?
Yeah, it will depend on F, of course. Yes, definitely. But okay, all this I'll try to make more precise. But what I'll try to be talking about in these lectures will be at least the first 2 points. And so maybe to start with, to get familiar with all this business, let me discuss Lanford's theorem, which is the derivation of the Boltzmann equation. Question 1 was solved in some sense up to some restrictions by Lanford in 1974. I guess what I want to do now is first, maybe as an exercise, before answering this question, is see what happens if time t equals 0. Okay, just a nice exercise, not too hard, to see what happens. I mean, this should look like F0, right? And then heuristically try to find the Boltzmann equation, and then I'll state the theorem. So let's see what happens at time 0. So consider this as an exercise. If it's easy for you, I hope you won't be too bored. But that way we just get a little bit used to those objects here. So I want to see what, let's say, the expectation of pi epsilon 0 of h. What does that look like? Okay, and I'd like it to look like the integral of f0 against h. So just to remember what that means, by definition, what I'm looking at is the sum over n of mu epsilon n over n. And then what do I have? I integrate over the domain. My function f, which I took n times. And then I'm told to compute the empirical distribution at time 0, which is the sum 1 over mu, the sum from 1 to n of h of zi dzn. So I'm sorry, this is very boring for some of you, but maybe it's not for everyone. So the first time I did it wasn't boring for me either at all. So let's do it slowly. But it's not hard. So now what I do here is just use symmetry of all those guys to see it's like the same thing as if I had n times h of z1, right? So when I have n times h of z1, this n becomes an n minus 1 factorial. Then I also have a mu epsilon n over mu epsilon. So what I get is the sum over n mu epsilon n minus 1 over n minus 1. And then I still have, oh, sorry, so now I'm cheating. If I didn't have this guy, what I'm saying would be true. Okay, so let's pretend I didn't have this guy. So then I get f0 of z1, h of z1, dz1, and I'm very happy with this. Why? Because if I didn't have this exclusion, remember z epsilon is exactly the exponential. Okay, so this goes away and I'm done. Okay, so I do have a slight problem because of this exclusion here. So I have to remove, so 1 minus this guy. So the error is, what happens if I'm not in the set d epsilon? What does that mean? Well, that means roughly that one particle, for instance, at least one particle, which I choose between 1 and n, is very close to another one, close at a distance epsilon, which means I have an epsilon d here. Okay, it's the error I'm making when I integrate it against that variable I've chosen, which is very close to another one. And then this compensates this 1 over mu epsilon very much, right? Because mu epsilon is epsilon 1 minus d. So this error term is very small. Here, and we will remember that later on, today or tomorrow, is that the exclusion at time 0 is not a problem at all, because you're integrating the volume of a ball of diameter epsilon, so that costs epsilon d, which is much smaller than 1 over mu epsilon, term. Right, so we're happy about what happens at time 0. Now the question we want to address is how does that evolve in time, and why does the Boltzmann equation appear? What I suggest now to find the Boltzmann equation is try to pretend everything is easy to compute and try to just directly, so this is totally wrong, of course, and that doesn't work, but it still does, I guess, explain a little bit why Boltzmann appears, is let's just pretend we can compute the time derivative of this empirical distribution just by doing something very naive, which is this. Okay, and let delta is not the same as over there. Let delta go to 0, and that will give you a time derivative of f, if f exists. And let's just try to guess the Boltzmann equation. This is, I mean, you can't make a proof out of this at all, but it does show, I think, a little bit about the difficulties, I guess, of the problem. And it does show Boltzmann very easily, actually. So let's see. So let's compute the empirical distribution at time t plus delta minus what happens at time t. And so what happens is the following. What could happen is that during this small time, I have n particles and none of them have met. That could happen, right? The time is very, very small. So I assume here that there are no collisions between my particles. I'm just computing h at time t plus delta minus h at time t. And I assume my particles don't meet. Of course, they could meet, okay? So I have to add what happens if I have exactly one collision during that time interval between I and j and no other collision. So in that case, I have 1/2 of the same thing, but this time I sum I, j, and then I remove I at time t and j at time t. And then I have more than 2 collisions, 2 or more collisions. Okay, so this is inequality. I haven't done anything wrong for the moment. Now I just need to compute the limit of these three lines as delta goes to 0 and see what it looks like. Okay, so left-hand side, if I believe this guy converges to some function f, so some f of th, this will converge to dtfh, right? H doesn't depend on time anyway. So if everything is smooth, if everything's nice, if this has a limit, then the left-hand side will be dtf times h. So what I hope is that the right-hand side here will be the right-hand side of the Boltzmann equation. So is that true? So let's see the first term. I don't know if I have colors. Yeah, great. So the first term here, if I have no collisions, my particles are going in straight lines. The velocity is not changing. So the difference between the velocities here is 0. And the positions have just moved of delta v, right? Between time t and t and time t plus delta. So this is exactly v greater than xh, roughly at position z epsilon I of t. Okay, so this is great. This is exactly the right-hand side of a transport term of the Boltzmann equation. If you've never seen Boltzmann, you're about to. Okay, so Boltzmann starts with dtf. You integrate by parts minus, put that on the other side, dtf plus v greater than, put that in red, dtf plus v greater than xf. It's not equal to 0, so that would be just a transport equation. I have to understand what's happening to this term here. And this is, of course, much messier. Because I'm looking here, I forgot, I'm looking at here at a two-particle correlation function, actually, right? I'm summing the empirical distribution at two different points, right? So I could give a name to this. This is a two-particle distribution function. What I get here, so I'm going to start waving hands much more right now. So what I get for this second term is, I'll explain my mu epsilon here, 1/2. So just this thing here. Yeah, 1/2 of the two-particle correlation function computed at h of z1, let's say t plus delta. I'll just, instead of I and j, I have 1 and 2 plus h of z2 minus h of z1 at time t minus h of z2 at stop time t. It's at some time tau, let's say, which is a collision time. I don't know tau, unfortunately. It's deterministic, but it's some collision time. Before collision, z2 is just my integration variable, as long as I haven't collided. Then I collide and velocities jump, remember? So this z1 is actually z1 prime, or post-collision. I'm almost done here. And f epsilon 2 here is a two-particle distribution function. And now what you have to notice here is actually very simple. I know exactly what that is, right? It's just by Descartes' laws. I can change variables to put this on this guy here. And that was a little bit subtle here, which I won't explain too much, is that instead of integrating against z1 and z2 and saying there's a time where my particles collide, which is some time tau, which depends, at time tau, which depends on z1, z2, I can say, instead of doing that, I'm going to integrate, change variables, and say this integration here is the same. So you have to believe me here, and I don't think you're going to enjoy that very much. But so z1, z2 is dv1, dv2. It's also dx1. And instead of integrating over x2 at time 0, I'm going to integrate exactly where my particles collide. And this is exactly v1 minus v2 dot omega, where omega is on the sphere. So this is bad. I know you're not enjoying that at all, but it's a tiny bit. It's just a Jacobian. You have to compute the Jacobian, right? If I move x2, how does my collision move? It moves exactly like this. Okay, it's just a Jacobian, but I don't want to do it in front of you because I won't be able to. But once you've done that, then you're essentially done. So I guess I have to stop as well, right? Oh, right. So you're essentially done. Because what you get from here, just a tiny bit of belief, mu epsilon goes with this guy. 1/2 will go away because z1 and z2 are symmetric. And so what you get in the end is f epsilon 2, the two particle distribution function z1, z2. Okay, that was a z1, z2 prime minus, because of this minus, f epsilon 2 of z1, z2 times the function h z1 d, this distribution, which I call mu. Just believe this computation, the second term here gives you exactly that as delta goes to 2. And it's okay, you can sort of make this almost rigorous. If you have more than 2 collisions, then actually everything goes to 0 because having 2 collisions on a time delta costs delta squared. And so since I've divided by delta here, it'll just go away. Okay, so those things go to 0. This is totally hand waving. You can't prove that actually, but you can believe me that it should be true. And in the end, there is a theorem you can prove, right? But this is just heuristics to show you where Boltzmann comes along. What's the difficulty here? I have an equation on this empirical distribution, which is a 1-point distribution. On the right-hand side, I have a 2-point correlation function. This is that. And now what Boltzmann said, and he assumed that, he assumed he had a propagation of chaos. Okay, and he didn't prove it, he assumed it, saying that if 2 particles are pre-collisional, which is the case here, it's also the case here because my measure here is telling me that those 2 particles here are pre-collisional. If it's the case, then my 2-point correlation function looks like the product of 2 1-point correlation functions, which is exactly a propagation of chaos assumption. So he's assuming that as epsilon goes to 0, my 2-point correlation function factorizes. Okay, which is sort of reasonable. If 2 particles meet, maybe they haven't met before. But it's also unreasonable because there are so many particles that they've probably either met before or met a particle which has met a particle which has met that one before, right? So there's probably a lot of work to make this rigorous statement. It can't be true when epsilon is fixed, definitely not. But the hope is that when the number of particles goes to infinity, then that in the end is true. Okay, and this is the 1-point correlation function, which is exactly this actually, this function here. And so if you believe this guy converges to function f, then you've found the right-hand side of the Boltzmann equation, 2 of ff. By definition, is what we've written here. So it's f b prime x, well, b prime 1 x1, b prime 2 x2, minus f of z1 f of z2, times the cross section I've written before, v1 minus v2 omega, dv1 dv2 d omega. So of course this is hand waving, this is not a proof, but it tells you that it is true that if this empirical distribution converges to some f, then f should satisfy the Boltzmann equation. This is Boltzmann. And so what's hard in what I said, what's not clear? So this thing here probably was totally unclear, but can be made rigorous if you work a tiny bit in compute this Jacobian. What's not clear at all is this propagation of chaos, okay, which is assumed here, but we have to prove or derive properly the Boltzmann equation. And what's totally unclear is how do you kill all the other terms. So maybe I can state a theorem, which is Lanford's theorem. And I'll just discuss a tiny bit the statement and make some comments, and then we'll stop for today. And so the theorem is as follows. So let me state it properly. You give yourself your f0 and you assume it's continuous. And bounded from above by Gaussian velocities. Okay, and that's very important. Then there is a time t, which depends on those constants t0, beta0, and you actually you could estimate it, I think, by, if you want to have something concrete, I think this works. You have some universal constant c, and then you, okay, this power I think is correct, but okay, we don't care at all. Anyway, because there is a time t such that it is a fact that if I define the 1 particle correlation function, which I hadn't defined yet, by definition, This is linear in H. By definition, the one particle correlation function is given by this thing here. And this converges as epsilon goes to 0 or as mu epsilon goes to infinity to the solution of the Boltzmann equation. Which we wrote on the other blackboard. And this is uniform in space and time. Actually, you can do more than that, but that's enough for purposes. And so that's exactly what we said here, roughly. And he even does more. He also proves that if you take the n particle correlation function, like the 2 particle we saw before, but you could do that for any number of particle correlation functions, this converges almost everywhere, at least, to n copies of the Boltzmann equation, of the solution of the Boltzmann equation. Okay, at least almost everywhere. We can make this precise, but so this is saying exactly what you want. That's propagation of chaos, right? This is proved. It's not an assumption you make at all. And so let me just make some comments before I stop. I'm sorry, I'm a bit late. So I'll pretend it's questions I'm answering. So, oh, why is T not infinite? Okay, this is a very good question. But I'll stop after that. So the real big problem about this theorem is this time here. Okay, so maybe I should explain why it's a problem. If you want to do hydrodynamical limits, what you have to do, so I'm telling you have to, but you could wonder why, but what you should do is rescale this collision term here by something going to infinity, like not epsilon, because epsilon is taken, but some, I don't know, some alpha. Alpha goes to 0. Okay, that's the first thing you have to do. That's assuming you have a lot of collisions doing that. Okay, that's another way of saying that is that your mu epsilon, you've rescaled by this alpha as well. And now if you read Lanford's proof and you put this extra factor here, because you want to do fluid dynamics, what's going to happen here is that this will be true on a time T alpha, just by scaling. Okay, and now you want alpha going to 0. And of course you have a problem. Okay. And so I'll stop here. You can ask as many questions as you like, but the biggest problem about this theorem is that, and for a moment, in this generality, no one knows how to go beyond that. Okay. So I'll stop here, and what I'll talk about tomorrow will be fluctuations around this theorem, and maybe a bit of its proof as well. Okay, thank you very much.
Any questions?
So regarding the kind of tail conditions, so is this because of the Cauchy-Kovalevskaya
Yes.
nature of it? So
Yes.
that's the sharp rate to.
So I don't know if it's sharp. I know this is one I can compute.
Yeah. No, I meant about the assumption on the right-hand side, on the tails
this up there?
of F.
Oh yeah. I mean, what happens?
It's related to some domain of analyticity or something?
Yes, exactly. So there are several ways of understanding it, but yeah, the easiest way is just saying that you see in this cross-section here, you're losing V's. So your function space has to absorb all those V's you're losing.
Mm-hmm.
And since you're doing that an infinite number of times, okay, you could say you could remove one exponential probably, but you could maybe only put V, maybe. Yeah. And the T alpha is also exactly due to that. Maybe one way of understanding this T alpha, if you don't want to talk about Cauchy-Kovalevskaya, but just about something more ordinary, is that at some point you're going to solve the Boltzmann equation or this problem. You're going to pretend the right-hand side of Boltzmann is, what did I put here? 1 over alpha x squared. Okay, which is something we all do when we do nonlinear PDEs. I mean, most of us are very bad at nonlinear PDEs, and whenever we see the right-hand side, we have a lot of trouble using the structure of the right-hand side. If you want to use the structure, you find weak solutions usually, which is great. But this is not a weak solution context; it's a strong solution context. And when you're doing strong solutions, at least me, I have a lot of trouble using the structure of the nonlinear term. Okay, this guy here has a lot of cancellations. If you put a Gaussian in this guy, you get 0. If you put the initial data here, which is a Gaussian, we might talk about this tomorrow. The theorem, if you follow Lanford's proof, is as bad as for any initial data. You totally lose the fact that the Gaussians cancel this guy. At some point, you put absolute values. And so another way of, yes, that doesn't answer your question, but the question about this is due to the fact that it's worse than that because you also have a V.
I was just wondering, so like you assume that like the collisions between particles happen, like they hit each other and then there's some like omega that governs how like the velocities are exchanged. Yeah, just like I think I saw where you used that assumption, like in the derivation, but could you just like quickly, like conceptually, like where is it used in the derivation? Like on the right-hand side.
So I'm not sure I got your, I mean, that's exactly the collision law. So, okay, so maybe the answer to your question is, if I put a potential, this would be different. If I put a force in my Newton's laws, this would be given by a scattering of your potential. I mean, when you have a potential, your particles are going to move, and they're going to be deviated but not touching.
Yeah.
And this and the outgoing velocities, depending on the incoming velocities, will be a function here.
Okay.
Okay.
Oh, so it's like right there.
So it's exactly there.
I think in the case when the velocity the Boston is enough randomness, this is probably at the known should be true, right?
Yeah, if you have randomness in the Newton's laws,
yeah,
then things are much better here.
Yeah,
yeah,
so,
you have
even only randomness in the velocity is
yes,
still
yes.
So it's much harder when it's deterministic.
Yes, and sometimes it's harder. I don't know. For me, it's not harder because it's very hard when there's too much probability. But I mean, what people tell me is that if you put noise initially, then you have ergodicity and you're very happy, and things are easier. In the sense that the theorems are much better. That's the way you should put things. Yeah. So the theorems are much better if you have ergodicity in your original system. You get long time convergence, and so you get fluid mechanics in the end.
What role does the play this Gaussian decay of the initial density?
So it's important to solve, I could say, even to solve the Boltzmann equation, as far as I know, you have two ways of solving Boltzmann. Either you use the structure of the equation, you have renormalized solutions, or you forget that and you're close to a Gaussian. Okay, and close means you're that plus something small, and the something small usually is related also to that. The Yukai theorems or
don't ask for lower bound zone.
No, here I know this is positive, right? But I don't assume it looks like that. I just assume it's controlled by that. Okay, and I think it's it's a quite natural assumption if you look at Boltzmann from a strong solution point of view.
Are you saying you need it for the like well-posedness, local well-posedness of Boltzmann, or are you saying you need it also for the proof?
I need it for the proof.
Okay.
Yeah, unfortunately, so for the proof, we're not using the well-posedness of Boltzmann. We're actually constructing a solution. It turns out to be the same. But to prove that you're constructing a whole hierarchy of equations to solve them, you need this assumption here. And so maybe to answer another way your question, you could wonder, if I know my solution to Boltzmann is global, for some reason, could I do better here?
Yeah.
The answer is I can't do better here.
I also have a question from a virtual participant. Jacob, would you like to mute yourself?
Oh, hey. Hi, Isabelle. How's it going? Can you hear me?
Yeah, very well.
Okay, good. So yeah, maybe this is a silly question or something that you're going to answer in your next talk. Is this theorem expected to be true kind of in this generality with a longer time scale? We don't know.
Yeah, I think it's expected to be true in some sense.
Really?
Well, I expect, I don't know who, I expect it to be true at least. Maybe not for every single initial data at 0, but for most initial data. What I could say is that this theorem in some sense is actually quite terrible if you think about it, because I take initial data, which is tensorized, and I work very, very hard, or Lanford worked very, very hard to prove that the solution stays tensorized. Okay, and what you would expect, well, what I would expect that I don't know how to prove at all, is that if you take any initial data and you wait a long time, then it will become tensorized. So in some sense, we're looking at the stupidest thing where you initially you're like you want, and you prove you stay like you want for a very short time. But you would expect that for long times, everyone becomes like that because there's some kind of ergodicity in the problem, which I don't know where to find.
Right. Okay. All right. So I know that you don't want to talk about the randomness case, but okay. Well, maybe I'll just yeah. It just sounds like, so like when you add randomness, it's kind of like, are you adding randomness? No. Okay. You know, I'm not going to ask you. I'm just going to.
You can ask him. I won't have an answer. But just people who put randomness would put randomness, for instance, in the collision rule. Okay, so what people do, I think, is say, well, when my particles collide, their velocities are changed in a random way with a very small parameter, right? And when that parameter goes to 0 with epsilon, then you get fluid mechanics. I'm not sure where the camera is. Maybe it is.
I see. Okay, so do you think? Okay, so I guess maybe the problem the question I'm trying to formulate but can't quite formulate is, you said the theorems in that case were much better. do you expect that even in this sort of almost deterministic case, or essentially deterministic case that Lanford is considering, do you think that the theorem of Lanford can basically be extended to look the same as the random case?
Yeah, I would think so.
Generic initial F or something.
I would think so. I would like very much someone to point out where ergodicity appears, but I would think it's true also, yes.
Okay, okay. I guess that's what I was trying to get at with the Lanford question. Okay,
Yeah.
all right, thanks.
Thanks very much.
Isabelle, I just say here, here. So, I don't know anybody else.
There was another question.
No. Go ahead. Oh, I see. You see the propagation of the chaos problem. The randomness one, when the equation itself is random, I think was solved. But if you feed the randomness into your initial distribution, like your density will be controlled from below, conceivably it feed into the equation and give you a random equation. So it should be easier.
Okay, I'm not sure I got what you wanted to say.
Oh, so if your particle, initial particle is more random.
Yes.
Then I would think it's easier because it feeds into the equation, generated random equation in some sense.
Yes, I would think the theorem is better. Again, it would be easier for me, but it would be.
That's a harder problem.
I absolutely agree with you. Yeah, it would certainly be easier in some sense. At least the result will be easier to get.
Is that no? I didn't know that question.
Not in exactly the way you're saying. I don't think it's not.
Is there some kind of conditional statement that you can make about ergodicity of the underlying Hamiltonian dynamics that would give you longer time convergence?
I don't know. I'd like that very much. Yeah, that would be great. It would be a very, very good first step. I don't know that.
Basically, what you said was you didn't want anyone to ask you any questions about the random models.
No.
So we're all going to ask you questions about the random models. So I mean, so I know, people have done work where they randomize the initial data, or they force things. But is there a lot of work? This is probably true, but where you maybe randomize that kernel somehow? Like you say, okay, so you've done this symmetric thing where you're letting all the interactions happen at once, but you could maybe randomly pick different interactions to happen at different moments of time. Is that the kind of thing people have looked at?
I never seen that. No. You mean, okay, no, I don't know.
Just curious.
It could be interesting, yeah.
That's not your philosophy, right? Your philosophy is not to do.
It's harder, but my philosophy is that you have some kind of spontaneous ergodicity. At some point, something happens, and so you don't need to put it in the system. It will happen. What we'll see tomorrow, hopefully,
right, but that's because you're picking good initial data somehow, right? Or just not the bad initial data.
Yeah, I think it should happen for almost any initial data.
Right. Those are the bad.
And so one thing I can say is there's a spoiler for tomorrow is that what we can do is for the central limit theorem, you do get a stochastic equation actually, which is good. Well, which is good for people who like stochastic equations like you. But so it does happen for a purely deterministic system. The central limit theorem, the equation on the fluctuation field is random. So it does happen.
One question. So is there some kind of like the simplest kind of deterministic model for which you get the same problem as Lanford in terms of having a short time? What's this? Is there like even a simpler model than the hard spheres for which we have the same problem?
Is it deterministic?
Like a Lanford theorem, which doesn't go.
I think this one is the simplest.
It's the simplest.
Deterministic, I think, is the simplest.
Okay.
Potentials are, I think this is unfortunately the simplest.
Okay. Thank you.
Okay, wonderful. Well, let's thank Isabelle again for a very interesting lecture.